Whoa, cool.
All right, guys, so this one is, let's see. The limits as x goes to, trying to work backwards from the answer key here. Where you go? -2? Maybe you could read it off to me. Is it 8 minus 3x? And you have to prove this using epsilon delta. One of our favorite things ever. So you start with the side work. Now the proof is going to look like given epsilon greater than 0. Let delta equal something. So that if x minus -2 is less than delta, you're going to work it out so that you end up with f of x minus the limit is less than epsilon. So all this says is, as my inputs get really close to -2, my outputs should get really close to 14. I mean, that's really, really watering that down. Well, that's basically what this is saying. And that is what a limit is. So what's the side work look like? Where do I start with side work? Secant? Yes. You start with the answer. And then you try to recapture this guy so you can identify what delta is. Yeah. Yes. What does epsilon signify, guys? What is epsilon? Distance, I love it. So both epsilon and delta are an idea of close. So basically the idea of a limit is as I get really close to some input, the outputs get really close to the limit. No matter how close somebody wants me to be to the limit, I can find somewhere that always is in there. So we looked at some visuals back in section 2.4 to kind of see what this looks like. So again, there's some problems in section 2.4 that are pretty simple at the beginning that give you the graphs. Some of you guys are just not showing me, well, some of you are not showing me any work. So just telling delta equals this. You've got to show me something that you've collected from the graph. Don't just say, well, I can see it. No, show me what you're seeing. Show me what you're working with, all right? Show me what you've got. So, yeah, the limit there's some neighborhood. So if somebody says, I want you to, if this is supposed to be the limit, and I want you to be within epsilon away. I want you to be within this neighborhood. All right? I'm going to continue this on. So that really is the limit. So no matter how small they make epsilon, I must always be able to find some neighborhood around A so that all the inputs there lead to outputs in here. So as they squunch this down, I have to always be able to find a neighborhood. So if I thought the limit was actually here, obviously that was completely wrong. They want me to be this close to the limit, well all my outputs are in here, that wouldn't work. The idea behind section 2.4, almost too easy to believe. The work of section 2.4, a little freaky. On one level it's freaky because we're not used to epsilon delta, we're not used to doing things like this. On another level it's freaky because it feels like you're cheating. The side work feels like cheating. Yes or no? I mean, does anybody feel that way? You're like, I do the side work, which is easy, and then I just copy it backwards. Okay, that's construction proof. You're constructing what you need. I need a delta in response to somebody's epsilon. Somebody says, I want you to be this close. And we're like, all right, I'm going to make delta half that or a third that or whatever. And then I'll always be that close. So here I'm trying to construct what delta is going to be based on epsilon. So when they make epsilon smaller, my delta correspondingly gets smaller. So that it'll always stay within so much of the limit. However close they want me to be. Okay, so now the idea, I understand, it's a little bit freaky, but I'm hoping to God that you understand it's really just about getting close. And then the outputs have to correspondingly get as close as somebody wants me to be. That's the epsilon. Somebody gives me epsilon. I'm like, oh, thank you. And then I say, here's what my delta has to be, so I'm always that close. Whatever the hell you say epsilon is. So here, what's the steps from here? Bless you. Bless you.
Thank you.
Okay. Just we got to be a little careful. Hope to God you guys understand. How do these compare? They're the same. If you change the sign of the number on the inside, the absolute value makes it go back anyway. So see, I could do this a couple different ways. I could just say, well, that's the same damn thing as 3x plus 6. Because that's how absolute values work. I did not do an absolute value. I changed the sign of the inside number because the absolute value is going to do that anyway if it needs to. If you don't like that, you could be more specific. You could say, what comes out of here? -3. And what's left? Careful. X plus 2. And what's the absolute value of -3? 3. So either way you do it, you're going to get that factor of 3. And look, I've recaptured this now, right? So if I divide by 3, I now know what delta needs to be. What does delta need to be? Epsilon over 3. 1/3 epsilon, if that's what somebody's saying. Not 1/3. It's way too big. So now coming back to the proof, so that's your side work. Your side work, put it in a little. That's side work. This is your proof now. I need to see these words. Don't just do a bunch of calculations and just throw it at me, right? This is the proof. Give it epsilon greater. Somebody comes along and gives me this epsilon. Happens every day on the street. Here's an epsilon. Like, shit. What are we going to let delta be? Epsilon over 3. So if they give me, if they say I want you to be within 0.1, well, all right, we're going to let our inputs be within 0.1 divided by 3. 1/30. If they say let epsilon be 0.03, I'm going to say, okay, I'm going to let delta be 0.01. There you go. That'll always force my inputs to have outputs that are that close. However close they want me to be, I can always find an interval that makes it be that close, all the outputs. That will always work if my limit is correct. So now I just kind of repeat this stuff. We've got x plus 2. Let delta be epsilon over 3. Multiply by 3. I mean, you just basically recopy that backwards, right? Then you get 8. Now there. So I got f of x minus L less than epsilon. If I am this close to my my input, I then come out to be this close to my output, to my limit. Okay. So what are epsilon and delta? They're distances. They're an idea of closeness. So we're going to see that a few times this semester. We use epsilon and delta when I want to define a neighborhood. This is really funny. It's an actual technical term. A neighborhood around something. I'll say it's delta in either direction. That's one way to say it's close to something. Yes?
Another symbol is like a Greek U. What does that mean?
Where have you seen that? This is in statistics.
Like in terms of, or in the context of like domains and ranges, sometimes it would be like a fractal pair and then like a U in between everyone.
Oh, no. So this, something like this here. Yeah, what the hell is that? Union. The English word for this symbol is or. You or you. Hey, look. So the English symbol, the English word for this is or. What's and look like? Yeah. Looks like an A that lost its middle piece, right? Had a rough night, whatever. So this is how I say, if I said, what's the domain? You're going to tell me all the x's that work. These x's, or these x's, right? Why wouldn't we put an and in there? English is funky. If English is your second language, you know all too well. English is funky as shit, right? And won't work here. Because math tells you what and really means. It means it's numbers that are in here and in here. Well, what numbers are in here and in here? Anything? No. So then you're basically saying nothing works. So that's why we use or. What can I use? Numbers in here or numbers in here? Oh, okay. Or lets more things in. When I teach or and I say or is the nice bouncer, and is the mean bouncer. Or it's like you got to know Joe, or you got to have a lot of money, or you got to dress nice. And I'm like, I got no money, don't dress nice, but I do know Joe. Anything I do? So or lets more things in. Cool. All right. Where to next? Yes. Oh, okay. I like it. So normally the two big weirdness things are epsilon delta and squeeze theorem. On the few pieces of homework I've gotten so far on this, there's not enough work shown. I'll show you. Which piece of that is bounded?
Sine.
Yes, so start with that. So sine of 3 over x minus pi, right? That piece, and they're just going to pull out that piece. The question is, what's the limit as x goes to pi? What the hell was it? X minus pi cubed times sine of 3 over x minus pi. What's that limit?
Negative 1 and 1.
Oh, that's not the limit. So that's the question. So what I'm going to do is I'm going to pull the piece of that function out that is bounded already. Because the whole idea of the squeeze theorem is I have my main function that is bounded between two other functions. And then I squeeze them together like the hydraulic press terminator. And of course this is bounded between negative 1 and 1. It's pretty cool with it. It don't matter what the shit's in there. It does not matter. The outputs will always be between those two. Now, how do well, that's not my function. What do I have to do to all the sides to regather this? What am I missing? X minus pi to the third. So I'm going to multiply the whole thing by x minus pi to the third. A little bit of wobbliness about what I said, but so now I've constituted my function that I'm really curious about. And what is it that I'm curious about the function? Now what do I do to all the sides to really recapture the question? I take, what's the only thing I'm missing now from the question? I've got this, I'm missing the limit. So now I take the limit, so now I take the limit as x goes to pi of this, limit x goes to pi. The inside, that's my question. Let's say equals limit x goes to pi, this side. And of course what happens on either side, if the limit here is 0, and you plug a pi in, this is continuous. You plug a pi in, you get 0. The other side, you come with less than 0. Same thing, right? So whatever's in here has got to be greater than or equal to 0 and less than or equal to 0. So what's the only thing it can be? Freaking 0. Right? So, and what's in here is my question. Thank God. So then I know the answer to my question then. Okay, I like it. Are sine and cosine the only functions that are bounded? No. So I could give you other functions that are bounded, but you just took that piece off. Why are you allowed to do that? Because you're not working with this yet. You're creating this. See how I created it? And now I can see what the answer is. I'm not doing something to this. I'm picking the part out that I know something about, and then I'm making this show up. Yes?
What's on the board? Is that would that be enough work?
Totally. Yeah, I mean, so right here, you want to, at the end, you want to say limit x goes to pi, blah, 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 equals 0. So some people just got to jump to here and like, how the shit do you get there? You got to show me a little bit of something. What are you building off of? Yeah. Just so I can be sure it's you doing it and understanding it. All right.
Another kind of chapter 1 concept, but piecewise functions.
Yes.
Okay. Specifically, like in the example, all right, 3 piece. First one is just x. If let's see, the domain is 0, is less than or equal to x, is less than or equal to 1, and then 2 minus x if 1 is less than or equal to, oh no, I'm sorry. 1 is less than x, or less than equal. Lord, I'm not talking about. 1 is less than x is less than or equal to 2. And then 0 if x is greater than 2. This is kind of like a syntactical thing, but why wouldn't it be 1 is less than or equal to x?
Because then, well, in this case, piecewise functions all the time have to be functions. So the problem is, what could possibly happen with a piecewise? Maybe it jumps. And if you have an equal sign on both sides of that jump, is that a function?
No.
No, because now it doesn't pass the vertical line test.
However, in this example,
In this specific case,
yeah,
it does have the same value, but that doesn't really matter. You have this guy does not exist at 1, this guy fills that hole in. You can't have 2 different definitions for a input. So I know they fill each other in, but still technically that's not really a function because you have 2 different definitions at that point. At 1, what currently is the definition? F of x equals x for 1. Notice how though the open circle here, where does it want to be at 1? This wants to be at 1. So if I took that top row off, there would be an open circle at 1. This top row fills that circle in.
So given the graph, is this kind of like arbitrary under the side? Let's see, is equal to, you know what I mean?
Oh, I see. If they gave you a graph and it was something like parabolic, and then constant. Yeah, it's totally up to you. They didn't define it. You can't have that belong to both, but you get to choose which one it belongs to because you don't know what it was. They both would have the same output graph because you don't know which one filled that hole in. Is that decent? There still seems to be like some mystery as to how to graph this. Is it hard to graph x? Y equals x. Is that difficult? No. It starts at 0 and it goes to 1. Now, how do I graph 2 minus x from then on? Well, at 1, so what I tell people is you can make a little table of values. So this is for x, 0, 0, 1, 1. That's amazing. How about for 2 minus x? Am I allowed to plug 1 into that? But when I teach pre-calculus, I say, do this freaking thing for yourself. You see what that's saying? Let's plug 1 in and see where it wants to be. So I know where to put the open circle. Now, in this case, it is going to get filled in, but I don't know that in general. So where does it want to be at 1? Well, it wants to be at 1. Yeah. So there would be an open circle here, but there's already a point there. So it just kind of fits around it. Boop. And then it goes to 2. Now, what's the slope on this? Yeah, so we go down 1 over 1. Pop, right? Or you can make a little table. At 2, it would be at 0. Whatever sound effects you want. And then from then on out, it's 0. And again, this is a closed circle, right? Why is that a closed circle so far? Why is that a closed circle? It was allowed to equal to. I'm allowed to use 2. And now 0 can't use 2, but it is already 0. So again, it would be an open circle, but there's already, and then it would be 0 forever after. I mean, that's how you can make a little table of values and only use numbers you're allowed to use. Anything that you're not allowed to use, still plug it in, just realize that's where an open circle is going to go. Because they're not always going to match up. This could have been up here, open circle. That's how you deal with piecewise functions. That's it. Yes? 5? 6, okay. I was going to say 5 is still up. 6 is the one that says it's continuous.
Yeah.
Where is this discontinuous or?
No, why is it continuous?
Why is it continuous? Okay. So you have to, what's the point that's the most important point to check for number 6? Pi over 3. Now, why is that the most important point? Because each of the separate functions that are part of that piecewise function, what is true about them? What's true about 2 cosine 3x and negative 6, what is it, x over pi? What's true about those two in the context of the question? The question says, explain why this is continuous. What's true about those two functions? They are continuous. So that's why I only have to check out pi over 3. That's the only place they might not connect. Each thing by itself connects everywhere. There's no jumps or anything. Cosine is really nice. This looks gross, but it's really just a line, right? With slope, what? Negative 6 over pi. So don't make too much out of this. Oh my God, it's a fraction. Who gives a shit? It's just something times x. It's a line. That is certainly as sure as all hell continuous. So that neither function has a problem itself. You just have to check out then the joint that they connect correctly there, right? They weld that thing well, or did it come off? Ah, shit. How do you do that? How do you check? Now, why technically can't you just plug it in? What is this defined for? Less than pi over 3. Are you allowed to put a pi over 3 in then?
No.
Not technically, right? And this one is? All right. So technically, and in fact, what's the definition of continuity? What's got to be true for a function to be continuous at a point? The limit from both sides have to agree, and they have to agree on the actual function value, right? So the limit as x goes to a has to exist. The only way they can exist is if they agree on it, right? And not only do they agree on where they're going, but the function agrees too. The function is like, oh yeah, I'm there too. This by itself, there could be an open hole in it, right? You add this in, oh shit, now it actually gets, it looks like it's going there, and it goes there. Oh, that's continuous. So how do I really investigate this? Limit as x goes to pi over 3 from below. What would that be? Which one am I using then? Yes, this one, because that's for below pi over 3. So that's going to equal 2 cosine 3 times pi over 3. And again, why am I allowed to just plug that in even though it doesn't get there? Because this is a continuous function. So if I plug it in, I see what it looks like it's going to. Do that. And what about the limit as x goes to pi over 3 from above? Of course, I have to use the other dude. Okay. Just to warn you guys, I'm pretty sure I'm going to make this a two-part test, where the first part, no calculator. The second part, you can take your calculator out and use it. Not meaning you do all your work on your calculator, but you can certainly do something, right? First part, I need to do some trig stuff, some other stuff that I don't want you reaching for the calculator, just to make sure you know how the hell to do it yourself. So now it's you that deserves a passing grade, not your calculator. Yes, Jeff, it's a very teacher thing to say. Screw it. Is everybody cool with that? I mean, you just do it. And what's supposed to happen? If this is going to be continuous, these have to be the same so that they actually connect. There's a bridge there, not this. Okay. So the kind of questions you can ask Daniel are, I really don't understand this process. Go do some examples doing this, like the limit definition of derivatives. Everybody cool with that? You know that sucker's going to be on there. How about finding the equation of a tangent line? To be really blunt, this should be pretty easy because we've done that stuff in algebra. It's not different from algebra, really. The only different thing is we use calculus to get the slope. It's really the only difference. No, I mean, I wouldn't give you, I don't think you had anything above a cube in the homework, did you?
Yeah, there's like multiple.
Oh, okay. No. So you could use, so if you have to do f of x plus h, and your function is x cubed, you could do that Pascal's triangle thing last time, right? This time, don't forget your coefficients. So it's all x's plus 3, 1 less x, 1 more h, plus 3, 1 less x, 1 more h, plus 1, all h's. Now real quick, why does this make sense? Because if I were to multiply this out, come on. This really just captures all the different ways to get, for example, how many different ways is there to get x squared h? 1? You guys see that? X squared h. How else can you get x squared h? And how else can you get x squared h? Do I have another color? Yeah. How else can you get x squared h? How many ways is there to get x squared h? 3. If I added one more, there would be 4, holy shit, and then you do the same thing. So this just captures that idea. So it says, don't multiply this shit out. Just realize what's going to happen ahead of time. Most shortcuts are just realizing the pattern of what's going to happen every damn time. So if you're curious, what if you had this? 2x minus 5 cubed. So here's the pattern. It's all the first guy. Plus 3 times 1 less of the first guy, 1 more of the second guy. Plus 3, 1 less of the first guy, 1 more of the second guy. Plus all the second guy. Like that. Why? Because that's what happens when you multiply this shit out. Now, and then you just simplify each of those, you're done. That's a hell of a lot quicker than 2x minus 5, 2x minus 5, 2x. Now, if you don't like this, if you don't like Pascal's triangle, you're a little crazy. That's all right. You can still write this 3 times, multiply it out, no problem. Yes?
So it's something about, like you can find the Fibonacci sequence.
Yeah.
I tried that.
All right. I'm not going to do it right now, but if you go diagonally, and you have to write a decent number of elements of Pascal's triangle, you could see Fibonacci sequence. There's a course I teach, Math 120, where we focus on the Fibonacci. Has everybody heard of the Fibonacci sequence? Real quick little aside. You guys know the Fibonacci sequence? You know it, don't say anything. What's the pattern? 2 is 1 plus 1. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. What size note cards do you guys get? What size note cards do you get? When you have a teacher that says, put your notes on a note card, because I'm an asshole. Put your notes on a piece of rice. Oh, sorry. When I teach a class that I'll have formulas, I say, bring in as much freaking paper as you want. I don't give a shit. Just don't bother other people. Right? This whole note card. Hey, you can have notes on a little tiny piece of that shit. Don't we have 3 by 5? 5 by 8? Or 8 by 5? Right? So Fibonacci is really neat. The sound, the sounds that are pleasing to our ear are made up of frequencies that show up in the Fibonacci sequence. The sound of an alarm clock in the morning are not in here. So you could take a whole lifetime to study Fibonacci because he's got connections to the stock market. A friend of mine used the Fibonacci thing about the number of peaks and valleys, and it kind of predicted for him when to sell and when to buy. And he made money throughout the recession using that. Right? You can use Fibonacci art. A lot of art that just looks good to our eye has ratios that come from the Fibonacci sequence. Enough of Fibonacci sequence. That's not going to be on the test. Sorry, I took a little aside, but it's good shit to know. Oh, okay. Well, see me now. I don't want to. I've spent too much time on Fibonacci. You guys want to something else? Homework, practice, test, yeah.
Can you first talk about 36 on 2.8?
36 on where?
36 on 2.8.
2 point.
It just has to
Eight?
make a, yeah, it has to make a table, and I'm not quite sure like how to estimate the values.
Okay, so let's see. So if they give you like points on the graph of n of t, right? So for example, so this is using the idea of secant lines. I could actually approximate the slope at 2001. How can I do that? So this is n of t. And prime. Why did I pick out 2001? What's interesting about 2001, it's between these two. So if I find the slope between these 2 points, that's an approximation for the slope at the point in between. That's the idea of secant lines. So if I want to know the slope here, well, I find the slope between these 2 points on either side of it, and that's a good approximation for the slope there. See how it's just shifted over? If I just move it down, that's a decent approximation. The freakier my function is, the worse that approximation is if I get too far away. But in general, that's a decent way to get an estimate. We saw that early in chapter 2. The whole idea of secant line, approximating a tangent. Why did we need secant lines? Because the formula for slope requires 2 points. That's what kind of built the entire way we do derivatives. So what would the slope be here? How do you figure it out? Yeah, so it would be 4897 minus 5,500 divided by 2. Yeah, and then keep going. So you can figure out the slope at 2003, 2005, probably. Yep, they give you all the even years. So you can approximate the slope at the odd years.
It doesn't specifically ask for that.
Well, they give you the even years, and they don't ask. Construct a table of estimated values for n prime. So it didn't say using the same inputs. That would be very evil. Because, and do you see why they gave us even years then? Because now I could use these to approximate this. I like it. So in real life, we don't always have a function that it represents the observations we make. We just have a bunch of observations that we made. And there isn't really a function that fits it nicely. We can still do things like derivatives. Or, at least estimate what the derivative is. We'll see that later in this course when we start doing antiderivatives. The same kind of thing works. We're doing the opposite of derivatives. Is that decent for that problem? The first part is just the meaning of n prime. That's the second part. The third part is just graphing the two. How are we feeling about what we did last time with given a function, can you graph its slope? I think I went pretty well over that. You guys seem to have gotten that pretty well. It's a really freaky thing in your head. You just start to trace the function, but you're stopping, you're saying, what's the slope? If it's negative, then you're going to put the slope down here in the negative area. That's what's got to click in your head. It has nothing to do with where the original function is. It has to do with what the slope of it is. Yeah?
What we learned, not yesterday, Tuesday, is that basically just graphing the derivative function?
Oh, the given an f, graph f prime? Right? Given an f, graph its slope? Yes, you're just graphing f prime. So when we learn the shortcuts for derivatives, you can go back and say, well, that's easy now. Because if I'm given a function, I could just take its derivative and graph it, and I'm done. We don't know the shortcuts yet, officially. I don't want to see any shortcuts for derivatives on this test. We don't know any yet, officially.
Can you do number 9 from the practice test?
Oh, all right. This is exactly, this is bread and butter stuff right here. This is, we're going to see this a lot this semester. Because it's a huge idea. Do you know people that could, estimate the square root for any number? Yes, okay.
No, not me, but my cousin.
You know somebody, that's what I'm saying. I wasn't going to put you on the spot. Oh, yeah, what's the square root? They use tangent line approximations. Because what's easier to do, a square root or a linear function? Linear function. What's the square root of 814? Well, what's 1/2 of 814 minus 814? I could do that in my head. I could do that pretty well. I can't do square root of 814 in my head too well. And maybe. So the function they give us here, what was it? Where'd it go? X cubed minus 2x? Is that the one for number 9?
Yeah.
Okay. I gave all my practice tests away, so bear with me. All right, this is exactly what I was talking about earlier. Do not just put underneath here f prime of x equals 3x squared minus 2. Oh, you took calculus before. Good for you. I don't care. We don't know that shit yet. Go away. That is going to be the answer eventually, but you have to get there the right way. You have to get there using limit definition. What the hell is that mean? Limit definition. Who goes to 0? H. And again, it's just x, go a little bit away from it. Here's f of x. Here's f of x plus h. All right, so I'm trying to get the slope at this point. So I step this in. So I get a slope between these two, but I'm letting h go to 0. So I'm letting this point get closer and closer. So every time I move, when I get closer and closer, that it really gets a lot better. And I'm letting it go to 0, so I get the exact answer. Why can I always use algebra? Y2 minus y1, blah, 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 because there's always 2 points. It never does go to 0. It just gets stupid close to 0. That's why we did all that work on limits, just so we were able to fully understand them, so we can build derivatives. So what is f of x plus h? We did that a minute ago. X cubed plus 3x squared h plus 3h squared x plus h cubed. I like it. And then minus 2 times x and minus 2 times h. Right? That's f of x plus h. And then you've got minus f of x. Get out of there. Minus x cubed minus 2x. So one thing is people kind of forget. They feel like, I've written enough shit. That must be everything. No. You forgot to subtract f of x out. This is never going to work. And this is all going to be over h, because this is the difference in the x's is h. So what is it that's supposed to happen from this step to this step? How do you know you're on the right track?
To go with the H also.
Yeah, everything without it, h should cancel so that the h's can cancel. The reason I get indeterminate form here is because there's an h and an h on the top and bottom. I want them to die, so I have to uncover it. Go away. Go away. Now I can divide everything by h. Oh, yeah. There you go. Right, just everything loses an h. Divide everything by h. And now I do this. You do get 3x squared minus 2 the correct way. What is this? What do I put here? What's the real symbol to put here? F prime. I love it. Because that's f. I did this process, so I found out its slope everywhere. That's f prime. And now is it the next? No, it's the same problem. Okay. So what does this problem really want from me? It wants the tangent line. I think I just did 8. Oh well. Now this is 8. 9 says, what's the tangent line to x cubed minus 2x at, was it negative 2, negative 4? Is that right? Okay.
Yep.
Yep. So find the equation of the line that has a slope, the correct slope at negative 2, and it goes through this point. That's an algebra problem. How do we get the slope? How do we get the slope?
Y2 minus y.
No. Yeah, we just did all that freaking work over there. What point do I want the slope at? Yeah, when x is negative 2. This is the slope anywhere. Where do I want the slope? When x is -2, I need to know what the slope is there. So in algebra, when you had a problem like find the equation of the line that is perpendicular to y equals 5x plus 7. All right, you got the slope by negative reciprocating that guy's slope. And then you plugged it in with the point, you blah, blah, blah. I'm going to do the same damn thing, except we're going to get our slope from our calculus work. Of course, what do you get here? 10. So you got the slope is 10. You got a point there. You could do mx plus b. You could do y minus y1 equals blah, blah, blah. Whatever you want. Or you can do Jeff's weird ass shit. You can say, well, that's going to have to be 10x. But when I plug a -2 in, I get -20. What do I do to that to make it become -4? -20 plus 16 is negative. There you go, done. I don't have to do any b shit or any y minus y1 shit. You can if you want to. Don't get me wrong, I'm sorry. From my perspective, I'm like, I want to do the least I have to, which means I have to understand more. The more you understand, the less you have to do. But there's nothing wrong with doing y minus y1. There's nothing wrong with it at all. It's still valid. Nothing wrong with it. Okay. How could you check this? What is this supposed to do? What is this thing? Beautiful. It's supposed to touch this graph at this point and kind of follow that graph at that point. So if you plot this and this, you should see that happen. So whatever this thing looks like, so at -2, when you plot this and you plot 10x plus 16 and you plot the function, it should look like that at -2. Yes?
I'm trying to confuse
Yeah. So that's why I said on there, I think I said, on number 9, I said, look back at your work for 8a, right? Find the equation. Okay, so 8a, we found this guy's slope everywhere. So now I can find the slope of this guy anywhere I want to, just by plugging the right thing in here. Really, once you find f prime of x for a function, you've got that function's number. You know its slope everywhere. Just plug in the right x to get the slope. So to find the equation of a tangent line, one big thing I need to know is the slope at the point.
Okay, what we meant to keep in, when we're getting the derivative function, at -2x minus 2h, why wouldn't that be plus 2h?
Oh, so f of x plus h is x plus h cubed, which is all this business, minus 2 times x plus h. Distribute. So f of x plus h.
Yeah.
Plug an x plus h in, you got to distribute the -2, that's why they both become negative. Cool, I like it. That's why I highly recommend when you're doing this, you focus on f of x plus h by itself first. Just focus on that, because if you try to do everything at once, you can do these little crazy little mistakes. There's too much shit going on at once. Build f of x plus h, then throw it in. Number 11, what's up? Yeah, I just want to see a graph. Yeah, so there's a lot of answers to that question. I think it's the one that I said limits have to be something, right? And there's one function value I gave you. So if I said the limit at 1 has to be 2, then you could do, there's a lot of different ways you can make it look like that. You can make it look like that. You can make it look like that. You can make it go straight. You're like, I want the boring function answer, right? So you got some leeway. Just please, whatever you do, make it a function. Oh shit! I get people that go, look, that's not a function. You're gonna lose points. Shit. So if you want to be really careful, you just always make a straight line limit. You know, very boring, but it's still an option. Is that enough? Is that cool? So there's a lot of different answers, but at specific numbers, at specific x's, certain things have to happen. So the limit as x goes to 2 has to be 7, so I must see an open circle at 7, and I must have both of them coming to, so it could come from, I don't care which way, right? Is that, yes? 10C. Oh! One thing about 10C, people sometimes run right past the negative exponent, I've noticed. What was it, infinity? So how could I rewrite that so it doesn't have a negative power?
1 over
It'll be 5 over, yeah, this goes down. So if you want to do it, like I said, this will be 5 over big freaking number, which goes to 0. Like 5 divided by big goes to small, goes to 0. So what would this be? Yeah, because what's happening, when you plug negative big in here, you get 5e to the positive big freaking number, right? So that's going to be 5 times stupid big gets stupid big. So what made this small was the negative power here. If my inputs are all negative, that negative goes away. So now it just becomes 5 times e to the 3x, really. So it just gets 5 times big. What is this? Let's see, here's something. What is the limit as x goes to infinity of sine pi x? This is a type of